In architecture, as in calculus, form and shape are everything. Every building is designed from its spaces and surfaces for its function and its appearance. For example, I'm standing in front of St. John the Divine right here. Obviously, functionally, it's a structure for worship, a place of religious significance, but visually, it's a lot more than that. You can see it captures the eye through, obviously, a lot of the neo-Gothic design there, a lot of its artwork, a lot of its stained glass work. Everything is built to capture the eye and to create that sense of power that allows it to function as a religious building. Naturally, you can obviously understand that figuring out how surfaces work through the use of calculus has changed the way that we design structures these days. For some of the most resounding of those changes was revolutions in architecture itself. We can look no further than something we've been studying in Calculus 3: quadric surfaces. These surfaces include paraboloids, hyperboloids, and of course ellipsoids, one of which caps the cathedral behind me, as we'll be talking about later. These shapes, in all of their complex and diverse forms, were really brought into the forefront of architecture by the work of people such as Gaudi, who built the Sagrada Familia, and in general changed the way that we look at surfaces in architecture today. But before I can talk about them, we have to go all the way back to the very beginning of architecture and the very beginning of construction itself. The very first quadric surface to probably be built was some sort of ellipsoid, probably a partial ellipsoid understood in calculus as a portion of the graph of x squared over a squared plus y squared over b squared plus z squared over c squared equals 1 for, obviously, constants a, b, and c. You can probably see that somewhere on the screen right now. In architectural terms, this is, simply put, a dome. Domes are truly ancient. Small domes probably appeared in Neolithic settlements in Sumeria, and larger brick and stone domes probably appeared there as well later on, as well as in Egypt and in other civilizations as early as 4 or 5 millennia ago. Dome roofs have, obviously, a variety of purposes that make them quite useful. They are very good at deflecting rain, for one thing, and effectively dispersing the elements overall. And since they are round in shape, and thus can be put on top of a round structure, building them requires fewer materials than building a rectangular roof on top of a rectangular structure. The construction of these ellipsoids began to shift away from function and more towards spectacle, awe, the sort of grandeur that you see behind me here. The Romans had a particular fondness for domes. They built the large Pantheon in Rome itself, which was the largest dome on Earth until the 1500s. And this fervor didn't exactly die down after that. In Islamic architecture, they became very prominent. Same with later European construction, for example, the Duomo in Florence. Even today, classical domes remain immensely popular. There are several here in Manhattan, one on top of Low Library back on campus, and of course one here on top of St. John the Divine. Sort of see it up there. In every single one of these examples, from Mesopotamian times to modern times, the dome has been selected as a sort of symbol of symmetry, of perfection. All of that a product of its mathematical nature, the first quadric surface to have made an appearance in architecture.
So, we're back in the classroom. Following the appearance of domes, hyperboloid surfaces made their debut in architecture in the most recognizable form, the whimsical cone. These shapes' mathematical definition actually predates their major use in architecture, where they were first discovered by Archimedes in 250 BC. Now that's a long time ago. As you can see in the image here, it was really hard for our modern-day archaeologists and mathematicians to actually date these structures and the early signs of which these shapes were first discovered. Several centuries passed, and they were found in places like roofs of minarets in the Islamic world, and also castles and towers within medieval Europe. These cone-like shapes proved just as good, if not better than domes, by draining water and snow effectively through their elements of slope, and served to elevate a space within their lofty elevation. But even while these structures flourished from antiquity to the modern era, they would be only what quadric surfaces to do so. Nobody actually knew what a hyperboloid or a hyperbolic paraboloid was in ancient Rome, not even the emperors like Nero, who set their own city on fire. Domes and cones may have found a spotlight millennia prior to their consideration through calculus, which was later discovered by earlier scientists. But it would take a modern understanding of quadric surfaces and a new approach that would then jump to the construction of others that would be integrated into today's architecture. So, let's jump to the present to see how Antoni Gaudi and a bunch of other architects were able to come up with better ideas and understand these elements of calculus.
Next, let's step into the present, where quadric surfaces are aesthetic representations of the intersection between maths and art. Few architects capture this connection better than Antoni Gaudi. His buildings, like La Sagrada Familia and Casa Batlló, demonstrated how quadric surfaces can be implemented to make organic, flowing structures.
Gaudi's work is particularly recognizable by his use of geometric shapes, including parabolas, quaternary arches, hyperboloids on one sheet, and hyperbolic paraboloids. His design process revolved around the question how constructions carried the most load with the least material to create impressive aesthetic spaces.
That's a good question. The answers he found were not guesswork, but mathematics. Quaternary curves for optimized weight bearings, paraboloids and hyperboloids for distributed vaulting and light control, and ruled minimal surfaces for practical construction.
And these geometric choices are visible across the nave, columns, vaults, and towers of the Sagrada Familia. His use of quadric surfaces, specifically paraboloids and hyperboloids, spread load efficiently across the surface and also shape how light and sound behave inside the church. He used paraboloid-like vaulting to create continuous organic ceilings where forces flow along the surface, and mathematically these shapes reduce bending and channel compression into the columns.
Hyperboloids of one sheet are especially important because they are ruled surfaces. Every single point on the surface lies on a straight line that moves along the geometry. Ruled surfaces led Gaudi and later builders to approximate complex curvature using straight elements like stone ribs, timber formwork, or straight modelled pieces, which simplified fabrication while preserving the structural benefits of these curved surfaces. Detailed studies of Gaudi's geometry show repeated use of hyperboloids and hyperbolic paraboloids in windows, tower forms, and skylights, where the geometry both strengthens the element and allows it to be built from straight components.
One such way that architects and engineers visualized this before the invention of computers was through graphical statics. Until the 1950s, engineers and architects used graphical statics to calculate the forces on arches, domes, beams, and other structural elements. It did this by drawing vectors with a scale, in which the resultant force can be measured on the drawing. This technique was first pioneered by Da Vinci and Galileo, and then later systemized by Carl Coleman, which is a big part of the curriculum at the Barcelona School of Higher Architecture. And this worksheet is what Gaudi used to graphically calculate one of the arches in his famous church of the Colonia Güell.
Well, diving deeper into the structural specificity of these structures and surfaces, parabolic and hyperbolic surfaces perform completely different functions. Parabolic surfaces excel at efficiently carrying uniform vertical loads across a span. Their curvature channels forces towards the support, allowing long, slender arches and vaults with predictable load paths. Hyperbolic surfaces, on the other hand, including hyperbolic paraboloids and hyperboloids, which excel at resisting multi-directional forces due to the double curvature. This gives thin shell structures a remarkable stiffness and strength with minimal material. This geometric flexibility allows architects to create complex flowing forms that span large areas while remaining lightweight, producing visually dynamic and structurally resilient surfaces.
From an appearance standpoint, on top of the structural functions of such curves, they are also very visually appealing. Parabolic and hyperbolic arches are essential to Gaudi's style because of the striking qualities that they impart. Their sweeping continuous curves create a sense of upward motion, which guide the eye along the elegant fluid lines that evoke the verticality of nature and the heavens. Paraboloids, with their smooth concave surfaces, generate a feeling of enclosure while simultaneously suggesting expansion, which produces a delicate interplay of light and shadow, which, through his work, animates the space.
Well, hyperbolic forms, meanwhile, introduce complex branching geometries that resemble natural structures, trees, branching vines, and flowing rock formations, imbuing interiors with an organic, almost otherworldly rhythm. These shapes were repeatedly used by Gaudi because they allow spaces to feel both monumental and ethereal, merging structural clarity with a poetic, spiritual resonance that became a hallmark of his style.
Gaudi also loved quaternary arches because these are virtually impossible to distinguish from parabolas, and therefore many scholars merely lump them together as parabolas, but this is problematic because they serve different structural functions. Quaternary is a curve that a uniform chain takes under its own weight. So when you invert a hanging chain, you get an arch that carries a compressive force, namely gravity, with essentially no bending movement.
In architecture, compressive forces are forces that push inwards, pressing materials together, similar to the way that weight of a roof presses down on the supporting columns. These forces are central to structural engineering because all building loads are ultimately transmitted to the ground through compression. Elements such as columns, arches, and walls depend on the compressive strength to maintain stability and safely support weight.
Gaudi used this principle explicitly in his hanging chain experiments, in which he built scaled hanging chain models with weighted chords, subsequently photographed and mirrored the shapes, and then inverted those images to produce arches in bolts that naturally followed the aforementioned lines of compression. The following takes the shape of a naturally hanging chain, as mentioned, with the form efficiently distributing weight and minimizing stress. And this analog calculus lets gravity compute the equilibrium for him, and then therefore guarantee that the final physical product worked with a natural function.
Expanding this principle, that quaternary arches are ideal for distributed gravitational forces. This leads to another discussion regarding the strengths of his quadric surfaces. Let's return to considering the hyperboloid of one sheet. From a structural perspective, the hyperboloid is ideal for handling the aforementioned compressive forces. The curved geometry channels load along the structure's surface towards the base, so it can remain stable even when materials are built with thin materials.
And we can better understand this concept through level curves. Remember that the general equation for the hyperboloid of one sheet is as shown, and then the horizontal cross sections from y equals k yield ellipses. These ellipses change in size with height, and so near the waist of the hyperboloid, which is z equals 0, the ellipse is the smallest, concentrating the compressive forces at the base, while higher up, the ellipses expand to spread loads outward. And these level curves demonstrate how the hyperboloid guides forces along the curved surface to distribute weight efficiently from the upper sections to the foundations. And this can be further mathematically explained with gradient vectors. If you remember, the gradient vector at any point is normal to the surface, pointing in the direction of the steepest increase of the defining function. And geometrically, this means that the gradient indicates the local orientation of the surface and thus aligns with the natural path of compressive forces in the structure. For example, near the waist of the hyperboloid, the gradient is mostly horizontal, indicating that it is where loads are being pushed outwards toward the base. By studying the gradient vectors across the surface, architectures can visualize how the structure handles loads, which in turn optimizes strength while simultaneously minimizing the required materials to build the actual structure.
Well, these surfaces are all extremely effective, but how did Gaudi decide where to use which curve? The rule of thumb in his work is function-driven mathematics. Quaternaries are chosen for primary load-bearing arches and vaults where compressive equilibrium is critical. They are literal solutions to the static problems of a hanging cable inverted into masonry. Paraboloids, on the other hand, are chosen where a smooth, continuous surface is required to carry distributed loads and modulate daylight. For example, in vaulted ceilings and roof profiles, where curvature both resists compression and sculpts interior illumination. Hyperboloids and other ruled quadric forms appear where Gaudi wanted complex curvature that could still be realized using straight elements or repetitive modular parts. Inspired geometry, for example, in window surrounds, and in many of the upper canopy and skylight components. In La Sagrada Familia, the central canopy of vaults, the tree-like branching columns, and the upper tower combine quaternary-based arches and quadric vaults so that each element's geometry answers a structural and functional demand. Carry the load, reduce material, bring in light, and amplify sound towards the altar. Scholarly structural analysis and recent architectural studies of the Sagrada Familia emphasizes this pragmatic coupling of curves and purpose.
Now, let's move on to the future. Take it away.
After Gaudi, the most notable change in the architecture landscape was the introduction of computers. And moving into the digital age, rendering software emerged, revolutionizing the industry of architecture as a whole. Beginning as simple planning and blueprint software for two-dimensional floor plans, computers entered the 3D space in 1963 with the introduction of Sketchpad. After this point, computers could render shapes and, by extension, buildings as three-dimensional objects. Architect Frank Gehry, disappointed with the available architecture software, famously used CAD, computer-aided design software, for boats and shipbuilding to create fluid, unconventional shapes that could no longer be defined as simple quadric surfaces. However, architectural innovations involving quadric surfaces have continued into the present day. A 2018 paper by Andres Martin Pastor and Roberto Navarez Rodriguez utilized architecture CAD software to prove a new graphic conjecture and consider the potential architecture implications. Working with Archimedean principles, Pastor and Rodriguez proved that if two rotational quadric surfaces share the position of one of their foci at the same point, then the intersection curves between the two surfaces are always planar. The oblate ellipsoid and one sheeted hyperboloid are excluded. Through exclusive use of graphic analysis, that is, using 3D CAD software, a new conjecture can be formulated. Pastor and Rodriguez see the implications of this conjecture as opening more possibilities for the materialization of not only parabolic domes, but also for domes or architectural surfaces based on the use of any rotational quadric surface, as described previously, since the planarity achieved for the intersection curves is always a property that facilitates the transition into constructive components through digital fabrication techniques. To reach this conclusion, 18 additional existing graphic theorems are presented in the paper, some of which we see as architecturally significant in the same way that Pastor and Rodriguez see their new conjecture.
For example, Theorem 8 can be directly applied to architectural design, particularly in the work of Santiago Calatrava, whose structures often rely on the geometry of quadratic surfaces such as paraboloids and hyperboloids. The theorem states that if a flat slice cuts two surfaces and the slice curves are similar shapes, then any other curved surfaces passing through this intersection will also have the similar shape. In architecture, this principle enables complex intersecting forms to maintain visual and structural harmony. Calatrava's designs, like the City of Arts and Sciences in Valencia or the Milwaukee Art Museum, feature multiple curved surfaces meeting seamlessly. By employing geometric relationships like those in Theorem 8, he achieves smooth transitions between vaults and roofs, described where the sliced curves remain consistent and proportional. This use not only enhances aesthetic unity, but also aids in structural efficiency. Theorem 9 also has important implications for architectural design, particularly in the creation of elegant and structurally coherent curved forms. The theorem states that if two curved surfaces share a key symmetry plane, looking straight down onto that plane at the intersection shows a curve like a circle, ellipse, or hyperbola. In architecture, this means that the complex three-dimensional interaction between curved surfaces can be understood and controlled through simpler two-dimensional conic geometry. Santiago Calatrava often employs this principle in his work using projected conic curves to guide the rhythm and proportion of his designs. For example, in the turning torso in Malmo or the Jägermes railway station, the intersections between sweeping structural shells and central planes create projected curves that define the visual order and balance of the building. By relying on the geometric predictability of conic projections, Calatrava can merge art and engineering. Jimmy will now talk about the application of one of these theorems on a building in New York City.
The World Trade Center oculus in New York City is characterized by its complex intersecting curved surfaces formed from rotational quadratic geometries, such as paraboloids and related quadric surfaces. So based on the theorem number 12 from the paper, if two rotational quadratic surfaces with parallel axes intersect, then the orthogonal projection of their intersection curve onto the plane containing the two axes is an arc of parabola. This aligned well with the oculus design, where the ribs and shell can be interpreted as segments of such surfaces intersecting to create smooth parabolic curves, so it contributing to both its elegant form and structural coherence. Furthermore, the intersection planar and shaped like a parabola make it easier to create and build the parts using computers and machines. So because the curves are simple and predictable, architects and builders can design the pieces precisely and put them together accurately. So even though the overall shapes are complex, this helps turn complicated designs into real buildings more easily.
We know it was a lot of history and a lot of facts, but thank you so much for taking the time to watch our video and get to know a little bit more about the history of quadric surfaces in architecture. This is Bendy Buildings. Please make sure to like and subscribe.